Welcome to Module number 2. Module 2 is an overview of the mechanistic-empirical design concepts included in the PMED software. As a reminder from Module 1 on the course schedule or roadmap for the course, Module 2 is an overview of the mechanistic-empirical design concepts that lays the basic groundwork for the remaining modules. There are 4 learning outcomes for Module 2. The first is to list the key asphalt and Portland cement concrete pavement distresses predicted by the PMED software for pavement design. The second is to compute damage using the fundamental material law for fracture. The third is to explain and illustrate the response to distress relationship. In other words, the transfer function. And the fourth is to list the key mechanistic-empirical design concepts that form the basic framework of the PMED software. There are many reasons for using mechanistic-empirical based pavement designs procedures, and in specific, the PMED software. Some of the capabilities and benefits of the PMED software include the ability to directly consider different design features. In other words, it's not just about determining layer thickness. Many design features should be considered in determining an appropriate design strategy. Some examples for flexible pavements include determining the asphalt binder type for different climates and traffic conditions, asphalt mixture properties, both volumetric and mechanical, and how those properties can change over time, the bond between adjacent layers, and drainage considerations for unbound layers. Some examples for rigid pavements include the Portland cement concrete properties and how the strength and modulus of the mixture can change over time, dowels in joints, widened lanes, joint spacing, and erosion of the unbound layers. Another capability is the inclusion of comprehensive methods for handling and determining the impacts of climate, truck traffic, material properties, and design reliability on pavement distress and performance. In addition, the PMED software includes comprehensive methods for combining structural and material considerations or interactions in terms of performance, and the performance is based on pavement distress and ride quality that can be quantified or measured to estimate the reliability of a specific design strategy. Continuing with some additional capabilities and benefits of the PMED software. It directly considers different truck traffic characteristics in predicting pavement distress, such as axle load, axle geometry, tire pressure, truck speed, and seasonal changes in traffic, among other characteristics. Capability to incorporate current materials and, more importantly, evaluate newer paving materials with limited laboratory test and field performance. Directly consider the impact of drainage on the vertical movement of moisture in the pavement structure for asphalt and rigid pavement design, as well as subbase erosion specific to rigid pavement design. A very important capability is the quantification of the structural condition of the in-place pavement layers for rehabilitation design. In other words, estimating the in-place damage of the existing pavement to ensure the rehabilitation designs are cost-effective. And more importantly, the capability to extrapolate from limited laboratory and field tests as related to pavement performance for design. The process of how a mechanistic empirical based analysis is performed through the PMED software is schematically illustrated in this slide. The inputs to the mechanistic empirical based procedure are used to try and simulate as closely as possible the pavement structure, its layer properties, and how those layer properties change over time in terms of their impact on pavement performance as affected by climate and wheel loads. The enhanced integrated climatic model is used to estimate or calculate temperature and moisture changes throughout the pavement structure over time. All truck traffic is characterized by axle load, axle type, seasonal variations, among other factors. The layer properties are determined at construction, and then those layer properties vary throughout the design period based on temperature, moisture, as well as aging of the asphalt mixtures and/or strength and modulus growth over time for Portland cement concrete mixtures. The pavement response models is used to calculate critical pavement responses that vary from month to month and year to year. Examples will be included in the latter modules that illustrate the change in modulus of different layers throughout the design period. This consideration of changes in the pavement responses that impact occurrence of distress is important. The fundamental material law establishes the allowable number of load applications, which is truck type and axle type dependent, as well as being climate and seasonal dependent. The fundamental material law is used to estimate the damage of the pavement structure throughout the design period. The damage is used by the transfer function to calculate pavement distress over time. Different structural response models are used for asphalt and Portland cement concrete pavements. The asphalt pavement structure response model is based on elastic layered analysis, which is illustrated on the left side of the screen. An elastic layered analysis-based response model assumes the layers are continuous in the horizontal planes and carry a portion of the wheel load. In other words, the layer properties are equal in the horizontal plane in all directions. The deeper the pavement in the structure, the lower the impact of the wheel loads because the upper layers spread the load impact on the lower layers. The elastic layered analysis program, referred to as Julia, is embedded in the PMED software for flexible pavements. The Portland cement concrete pavement structural response model is based on finite element analysis for slabs on an elastic foundation, which is illustrated on the right side of the screen. A finite element analysis-based response model is used to simulate and include the impact of free edges, longitudinal and transverse joints, and cracks in the rigid pavement. The use of finite element analysis for rigid pavements allows the consideration of curling of the slab between daytime and nighttime conditions, which is important relative to performance of rigid pavements. The iSlab 2000 finite element program was used to generate the structural responses for the rigid pavement analyses. However, iSlab is not embedded in the PMED software. Neural networks are used to calculate the critical rigid pavement responses. The neural networks were developed based on the results of many iSlab computations. iSlab 2000 was used to calculate critical pavement responses over a wide range of site conditions, climates, truck traffic, and design features, among other input variables. The results from the iSlab 2000 were used to generate the neural networks embedded in the Pavement ME software. The neural networks included in the PMED software are used to predict the critical pavement responses for the rigid pavement fundamental material laws and transfer functions. The use of neural networks allows the program to evaluate a specific pavement structure much faster than using the actual iSlab 2000. The primary two rigid pavement responses in the fundamental material law for predicting rigid pavement distresses are corner deflections along the edge of the slab and stresses at the top and bottom of the Portland cement concrete slab. The critical rigid pavement responses are illustrated in the latter part of this module, as well as in Module 5 for each rigid pavement distress predicted by the PMED software. The following slides illustrate the computation of deflection and tensile stresses for different conditions using iSlab 2000. This screen includes an example of the deflections computed by iSlab 2000 across multiple slabs for a tridem axle load simulation on a flat slab. In other words, no curling caused by daytime and nighttime conditions. In comparison, this screen includes an example of the deflections computed by iSlab 2000 across multiple slabs for a tridem axle load simulation, but with daytime curling as the slab warms during the day. The deflections along the free edge of the slab are greater than for the unloaded slabs along the free edge. In addition, the edge deflections with curling are greater than for the flat slab condition without curling that was shown in the previous slide. The deflections between assuming a flat slab and considering curling caused by changes in the temperature with slab depth do make a significant difference, which is taken into account by the PMED software. This screen includes an example of the stresses calculated in the Y direction of the slab by iSlab 2000 across multiple slabs for a tridem axle load simulation on a flat slab without any curling between nighttime and daytime conditions. The highest tensile stress occurs under the center axle of the tridem axles and along the edge of the slab as expected. In comparison, this screen includes an example of the stresses calculated in the Y direction of the slab by iSlab 2000 across multiple slabs from a tridem axle load simulation, but now considering daytime curling as the slab warms up during the day. The highest tensile stresses still occur under the center axle of the tridem axle, and it is greater along the edge of the Portland cement concrete slab. In the previous example, the highest stress was only under the center axle of the tridem axle simulation, but with daytime curling, now the higher tensile stresses occur under each axle load of the tridem axle simulation as shown on the screen. The impact of curling is critically important in rigid pavement analysis and design simulations. Some of the structural response models for flexible pavements analysis are included on this screen. Julia is the elastic layered program that the pavement structure or software uses to compute critical pavement responses. Julia stands for Jacob-Bouzon Layered Elastic Analysis. Jacob-Bouzon was the developer of the Julia program. This screen is an illustration of the outputs from the WinJulia program, a Windows version of Julia. Many pavement responses are computed at different grid points under the axle loads and with depth in the pavement structure, as shown in the tabulation on the right side of the screen, but only a few of these responses are used in the fundamental material laws. The critical flexible pavement responses are discussed in the latter part of this module, as well as in Module 6, for each flexible pavement distress predicted by the PMED software. In summary, the primary responses for flexible or asphalt pavements include tensile strains at various depths in the asphalt layer, tensile stress at the surface of the asphalt wearing surface, vertical compressive strains in all layers simulated in the pavement structure, and foundation soils or subgrade, and horizontal and vertical stresses at various depths in the unbound layers. Remember from Module 1, the transfer function is the link or mathematical relationship between structural response and pavement distress. For all mechanistic empirical-based procedures, including the PMED software, this part of the framework is the key. Without an accurate link between the pavement responses and pavement distress measurements, cost-effective and reliable designs are not possible. There are two types of classifications of the transfer function: a direct translation and an indirect translation. The direct translation simply means the critical pavement response is used directly to predict pavement distress through the fundamental material law. The indirect translation means the critical pavement response is used to calculate damage through the fundamental material law, and the resulting damage then is used to predict pavement distress. The transfer function for the direct translation is simply the relationship between pavement response and distress. For the example on the screen, the elastic vertical strain shown on the screen is calculated in an unbound aggregate base layer using Julia. The elastic vertical strain is used to calculate the plastic strain, noted as epsilon subscript p in the unbound aggregate base, using the fundamental material law for rutting in the aggregate base layer. The rut depth, defined as RD, is calculated from the plastic strain in the aggregate base. The fundamental material law, combined with the plastic strain translated to rut depth, is the transfer function. The transfer function for the indirect translation is similar to the direct translation, except an additional computational step is required. For the example shown on the screen, the Portland cement concrete tensile stress is calculated at the top and bottom of the Portland cement concrete slab using the neural networks developed from iSlab 2000. The Portland cement concrete tensile stress is used to calculate the allowable number of load applications, noted as capital N, for the climate and the truck traffic axle load that cause the Portland cement concrete tensile stress. The damage index, noted as DI, is calculated as the summation of the actual number of load cycles of the truck traffic axle load in the climate divided by the allowable number of load applications. The damage index is used to calculate the percent cracked slabs in a jointed plain concrete pavement, noted on the slide as FAT-CRK. The transfer function is the damage index as related to the area of percent cracked slabs. Damage, as used in the fatigue damage transfer function, is defined as the percentage or decimal proportion or a ratio of the allowable number of load applications that results in a specific area of cracking. A ratio of 0.5 simply means 50% of the allowable number of load applications or life to a specific pavement condition has been consumed. Most mechanistic empirical-based pavement fatigue or fracture design procedures follow a concept referred to as Miner's hypothesis, which is defined on the screen by the equation. Large N is the total life or allowable number of load applications, and usually defined or measured through laboratory fatigue or fracture testing of both Portland cement concrete and asphalt mixtures. An example is used to demonstrate the fatigue damage concept using Miner's hypothesis that was defined in the previous slide, using an office item that everyone should be familiar with. This example is referred to as the paper clip fatigue example. In summary, take a paper clip and expand it out along the straight portion as shown on the screen in the picture in the lower left-hand part of the screen. Bend the straight portion of the paper clip to a defined angle as shown in the picture on the right-hand side of the screen. The bend angle shown in the picture for this case is 90 degrees. One bend or load cycle is defined as bending the paper clip to an angle and then bending it back to the straight line as shown in the picture on the screen. Count the number of bends until the paper clip breaks and record the number. Take another paper clip, but bend it to a different angle and count the number of bends until it breaks. The same procedure is completed for 3 to 5 bending angles. A video is included here to demonstrate this example of the number of bends to cause the paper clip to break. This screen summarizes the number of bends that caused a fatigue failure of the paper clip, in other words, causing it to break. The bending angle refers to a specific stress or strain applied to the paper clip and is similar in concept to the fatigue strength or failure of Portland cement concrete and asphalt mixtures. Calculate the average number of bends for each angle. These values are included in the table on the screen from the example. An important point to note relative to measuring fatigue strength of almost all materials is the variability in the test results or observations. That variability in the data is typically very high. The results from the paper clip example are illustrated in the graph shown on the screen. The equation represents the fundamental materials law for a specific type of paper clip relative to the size and diameter of the paper clip. The allowable number of bends or load cycles for each angle is tabulated on this screen, which were determined from the average data included on the previous screens. The average allowable number of bend or load cycles included in this table were calculated using the fundamental material law resulting from the example and illustrated on the previous screen. Using Miner's hypothesis, as defined in a previous slide, the damage index for each bend cycle of a specific angle can be calculated using the equation shown on the screen and previously discussed. The damage index, or the incremental damage index from one bend for each bending angle used, is calculated as the actual load cycle, or one bend cycle, divided by the allowable number of bends or load cycles, which is tabulated on the screen. The total damage for one cycle or each angle is summed and equals 0.142. Calculating the total damage for a combination of a different number of bends or load cycles is determined in the same way. The number of bends for each angle is tabulated on the next rows of the table, now shown. The damage from the actual number of bends is tabulated along with that damage for all bends or load cycles combined, which is 0.952. Thus, based on the average condition or a 50% reliability, the paper clip should not break. When the total damage exceeds 1.0, then the paper clip should break or fail. The incremental damage accumulation concept is explained in Chapter 5 of the MEPDG Manual of Practice, as it applies to both flexible and rigid pavements. You are encouraged to review that chapter prior to starting Modules 5 and 6 on rigid and flexible pavements, respectively. The next few slides provide a brief overview of the incremental damage accumulation as applied to the PMED software for rigid and flexible pavements. The incremental damage accumulation concept is used in the PMED software. Basically, the PMED software breaks the design period into intervals, and the actual and allowable number of load cycles are determined for each interval and site condition. The incremental damage index is calculated for each interval, and then all increments are summed to determine the total damage for predicting distress throughout the design period. The responses for each distress type and material are presented in the next segment of this module. The pavement types or design strategies for new pavement design included in the PMED software shown on this screen. For rigid pavements, jointed plain concrete pavements, and continuously reinforced concrete pavements are appropriate design strategies included in the PMED software. For flexible pavements, asphalt pavements consisting of conventional asphalt with the thicker aggregate base layers, deep strength asphalt pavements with thicker asphalt layers relative to the aggregate base layers, and full depth asphalt pavements are appropriate design strategies. In addition, semi-rigid pavements consisting of an asphalt surface over a cement or pozzolanic stabilized base is an appropriate design strategy. The next portion of this module will define the different distresses considered for each pavement type or pavement design strategy. The distresses computed using the PMED software for jointed plain concrete pavements are shown on this screen. All distresses for rigid pavements used in the PMED software are defined and measured in accordance with the long-term pavement distress identification. Joint faulting is a difference in elevation across a joint or crack and is measured in average inches. The PMED software combines the bottom-up and top-down fatigue cracking, but computes them separately. Mid-slab cracking is considered the fatigue cracks in rigid pavement design and are cracks that occur perpendicular to the pavement centerline. Normally, these cracks are recorded as a number of cracked slabs and reported as total percent cracked slabs. The International Roughness Index, defined as IRI, is also predicted for jointed plain concrete pavements, but will be discussed at the end of this section because it is considered a performance indicator that is applicable to all types of pavements and is not a specific distress type for a specific type of pavement. More importantly, no mechanistic response is used to predict IRI over time. The prediction model is just an empirical relationship. A description of the regression equation is included in Module 5 for jointed plain concrete pavements. IRI is calculated from joint faulting, transverse cracking, the initial IRI, and a site factor variable. The distress computed using the PMED software for continuously reinforced concrete pavements is shown on this screen. Punch-outs are closely spaced transverse cracks with a longitudinal crack. Punch-outs are usually recorded on an area basis between the edge of the pavement and longitudinal crack as shown in this screen and reported as the number per mile. The IRI is also predicted for CRCP, but will be included at the end of this section because it is considered a performance indicator that is applicable to all pavement types. More importantly, similar to JPCP, no mechanistic response is used to predict IRI over time for CRCP. The prediction model is an empirical relationship. A description of the regression equation for CRCP is included in Module 5. IRI is calculated from punch-outs, the initial IRI, and a site factor variable. In summary, the critical responses used to predict the distress for all types of rigid pavements, JPCP and CRCP, are listed on this screen. Tensile stress at the top and bottom of the Portland cement concrete slab are used to predict transverse or mid-slab cracking of JPCP. Corner deflections are used to predict faulting in JPCP. And tensile stresses on the top of the Portland cement concrete slab are used to predict punch-outs for CRCP. The fundamental material laws and specific transfer functions for Portland cement concrete pavements are included in Module 5. Before moving to the flexible or asphalt pavement distresses and critical responses, not all Portland cement concrete distresses are considered by the PMED software. Other distresses occur in rigid pavements, but those distresses are not used or considered in the design of rigid pavements. Many of these rigid distresses are material related that can be controlled through the material specifications and/or mixture design. Some of the other Portland cement concrete distresses include spalling, map cracking and/or scaling, pumping of fines, and blow-ups in CRCP. As you start to use the PMED software, give some thoughts and consideration to those distresses that are not mechanistic or mechanistic controlled and how they impact performance in IRI. Indirectly, some of the other distresses do impact the IRI growth or degradation in smoothness over time. As an example, spalling. So indirectly, some of the other rigid distresses are considered in the PMED software for rigid pavement design. Spalling is considered and calculated within PMED software, but is not used as a design criteria, so it is considered indirectly. The distresses computed using the PMED software for asphalt or flexible pavements are shown on this screen. All distresses for flexible pavements used in the PMED software are defined and measured in accordance with the Long-Term Pavement Distress Identification Manual. Alligator fatigue cracks are a series of interconnected cracks that form an alligator cracking pattern. These cracks start as short, longitudinal, and/or transverse cracks, and with continued wheel loadings, interconnect to form the alligator cracking pattern. These cracks are measured on an area basis and converted to a total percent of the lane area, and the total area does include the wheel path and non-wheel path areas. Rut depths are a longitudinal surface depression in the wheel path that can also include the transverse displacement of the asphalt mixture that forms a hump on each or one side of the wheel path. Rut depths are measured in inches from the bottom of the hump or depression to the top of the hump to a visual wire line transversely across the lane. The value recorded for a project is the average maximum rut depth between the two wheel paths. Transverse cracks occur perpendicular to the pavement centerline and are a result of low temperature events, thermal cycling, and/or shrinkage of the asphalt mixture. Transverse cracks are measured in length and recorded as total feet per mile. The International Roughness Index, or IRI, is also predicted for asphalt pavements, but is included at the end of this section because it is considered a performance indicator that is applicable to all types of pavements. More importantly, similar to rigid pavements, no mechanistic response is used to predict IRI over time for asphalt surface pavements. The prediction model is an empirical relationship. A description of the regression equation is included in Module 6. IRI is calculated from fatigue cracks, rut depth, transverse cracking, the initial IRI, and a site factor variable. In summary, the critical responses used to predict the distress for all types of flexible pavements are listed on this screen. Tensile strain at the bottom of the asphalt layer is used to predict bottom-up alligator fatigue cracks. Tensile stress at the top of the asphalt wearing surface is used to predict top-down alligator fatigue cracking. Vertical compressive strain in all layers of the flexible pavement is used for predicting total rut depth measured at the surface. And tensile stress at the top of the asphalt layer is used to predict transverse cracks. The fundamental material laws and specific transfer functions for flexible or asphalt surface pavements are discussed and presented in Module 6. Not all asphalt pavement distresses are considered by the PMED software. Other distresses occur in flexible pavements, but those distresses are not used or considered in the design of flexible pavements. Many of these distresses are material related that can be controlled through the material specifications and/or mixture design. Some of the other asphalt surface pavement distresses include raveling, bleeding, shoving, edge cracking, block cracking, and center lane longitudinal cracking and longitudinal joint deterioration. As you start to use the PMED software for flexible pavement design, give some thoughts and consideration to those distresses and how they impact performance and IRI. Indirectly, some of the other distresses do impact the IRI growth or degradation in smoothness over time. So indirectly, they are considered by the PMED software in the design of flexible pavement. As an example, raveling. Raveling is not calculated within the PMED software, but does have an impact on IRI. So it is considered indirectly through the site factor variable. The distresses computed using the PMED software for semi-rigid pavements are shown on this screen. The distresses for flexible pavements are identified by italics and in a different color, and are also considered for semi-rigid pavements. Reflection cracks are predicted by the PMED software for semi-rigid pavements. Reflection cracks include transverse and/or shrinkage cracks from cement-treated base layers and fatigue cracks from the cement-treated base layer. The transverse reflection cracks in semi-rigid pavements are measured as total length and recorded as total feet per mile. The fatigue reflection cracks in semi-rigid pavements are measured as percent total lane area. All distresses for semi-rigid pavements used in the PMED software are defined and measured in accordance with the long-term pavement distress identification manual. The IRI is also predicted for semi-rigid pavements and is discussed at the end of this section because it is considered a performance indicator for all types of pavements and is not predicted from a mechanistic response parameter. A summary of the different distresses and the critical responses that are used to predict the distresses in semi-rigid pavements are included on this slide. The same flexible pavement responses for new flexible pavement designs are used to predict the distresses for new flexible pavement designs shown in an earlier slide. Specifically for semi-rigid pavements, the tensile stress at the bottom of the cement stabilized layer is used to predict the fatigue or transverse cracks of the cement stabilized base layer itself. The tensile and shear stresses at the bottom of the asphalt layer above crack in the stabilized layer are used to predict both transverse and fatigue reflection cracks. Ride quality, as defined by smoothness degradation or roughness and measured by IRI, is the common performance indicator between all pavement types and overlays considered in the PMED software. It is important to incorporate and consider ride quality in design because ride quality is a major factor of concern to the user. This parameter assures the user of a smooth, comfortable ride over the pavement life. And while distress is a measure of structural condition, ride quality is a measure of functional condition. And it is a parallel to the well-accepted serviceability to performance relationship derived from the original ASHO road test. IRI is measured by different pieces of equipment shown on the screen and represents the cumulative differential vertical displacement within a specific horizontal distance along the roadway. The units of IRI are inches per mile. No critical mechanistic response parameter is used to calculate IRI. As such, IRI is predicted using empirical regression equations included in the PMED software. The IRI is dependent on the individual distresses for a specific pavement type predicted by the PMED software, the initial IRI at construction, and a site factor. All of the variables for the different pavement design strategies are presented and discussed in Modules 5, 6, 8, and 9. IRI is considered and predicted for the following pavement design strategies: flexible pavements consisting of conventional deep strength and full depth asphalt pavements, semi-rigid pavements, jointed plain concrete pavements, continuously reinforced concrete pavements, asphalt overlays of all flexible pavements, semi-rigid pavements, jointed plain concrete pavements, and continuously reinforced concrete pavements, and Portland cement concrete overlays of jointed plain concrete pavements and continuously reinforced concrete pavements. The key components of the MEPDG design framework were presented and discussed in this module and are listed on this screen in summary. In summary, the key components include the inputs to the PMED software, the failure criteria for each distress type for specific pavement design strategies, the design reliability for the pavement design, the structural response models, the fundamental material laws, the transfer functions, and distress prediction models based on Miner's hypothesis for calculating damage, and the smoothness or roughness determined by IRI regression equations. The key components are shown in flowchart form on the next slide. This screen shows a flowchart for the MEPDG procedure, which is similar to most other mechanistic-empirical based procedures. The framework is included in Chapter 1 of the MEPDG Manual of Practice and includes 3 basic sections: the inputs, the analysis or computations, and the outcome. You are encouraged to review Chapter 1 of the MEPDG Manual of Practice that describes in more detail or provides an overview of each of the segments and input variables, as well as computational strategies to define a viable pavement design alternative for a set of site conditions. The input categories include traffic, material, layer properties, climate, foundation, and design criteria, and that design criteria does include reliability. The computational analysis include the mechanistic component or the response model to compute critical pavement responses. For asphalt pavement, the response model is elastic layered theory, while for rigid pavements, a finite element analysis model combined with neural networks is used to compute pavement response. The damage computations and accumulation is based on fundamental material laws for specific materials. The transfer function is used in the analyses portion for predicting pavement distress. The outcomes are the predicted distress over time and used to select viable alternatives that meet the design criteria and reliability. The two key design inputs included in the PMED software to evaluate a specific design include design failure for distresses and IRI and design reliability. The design criteria are the threshold values that trigger some type of structural rehabilitation activity that excludes pavement maintenance and preservation treatments. The design reliability is the probability the design strategy will perform as expected over the design life for all distresses and IRI predicted by the PMED software. This ends Module 2. The next module of the training course sequencing is Module 3 on risk, reliability, and pavement design.